Hello and welcome. Here we are in lecture 16. So today we'll be talking about a few things. We're actually kind of shifting gears. So up until now, it's kind of been this model of teach you a little bit of Scala, teach you how to apply it to Chisel. Maybe we'll have some of those case studies like the queue design or the network design where we actually iteratively develop something. Um, the next few lectures are going to be less about exact code and more about kind of how do you go about designing things. So in particular, today is going to be about physical constraints and thinking about that a little bit. We kind of need to talk about it a little bit in order to make sure making hardware makes sense, as well as memory. And then the remaining lectures, of course, we're going to have guests from Jose on Friday talking about Pyro. On Monday, we're having another guest talking about formal verification in Chisel. The project meetings, then following that, we come back to the same topic. We have some more discussions about certain ways to consider physical design optimization within your Chisel. So today is kind of the kickoff for that new unit of this course, kind of thinking more about the whole physical process rather than just the high level, Chisel RTL. Okay, so as we mentioned, we're trying to give a pitch on physical design optimization, talk about memory, and then talk about some ways to improve memory. So this is a little bit more architectural today. Okay, so naturally the question is why are we talking about physical design? Why are we optimizing it? Well, efficiency, right? Um, at some point, you need to get efficiency, right? If you're not worried about efficiency, under some very broad definition of that term, you may not need to optimize. You may not even need to make hardware, right? That's kind of the point is, right? It takes a certain amount of time to develop hardware, as you've all learned in this course, even for Agile techniques, there's a certain amount of hiccups. And you know what? If your task can be done by writing code on a processor, you should write code for a processor, right? In the modern era, in 2023, you can buy, surprisingly few processors for even, a few dollars or a few cents, depending on the application you're doing, and they can get a lot done, right? So if you're saying, you know what, no, writing code is not going to cut it, existing processors are not going to cut it, I need to make some hardware. Well, that means there's some reason why you're doing this, right? It could be maybe you need really high performance. Maybe you need to be really energy efficient and last really long, like some sort of tiny embedded device that have one battery for the entire lifetime. Or maybe you're worried about cost. Maybe you want to have a very specialized chip you can make many of really cheaply, and that's going to do one thing, and you want to make that cheaper than you could buy an existing SoC kind of processor from someone else. But the result is the reason why you go through this effort at some level is because you want some efficiency, right? If you don't have that efficiency goal, don't bother with this, right? Just write software on existing microcontroller or CPU and be done with it, right? So depending on what your goals are, different metrics, different ways you go about it. But at the end of the day, keep an eye on, what is the cost benefit ratio, what you're doing, um, if you spend years and years and years building a chip and it turns out that the chip that does what you need comes out next year, well, was that worth it? Maybe not, right? And so, uh, like I said, the reason why I have this slide, not so much you shouldn't do hardware design, it's more just if you are doing hardware design, appreciate efficiency is a really important metric, right? That's why you're doing it. If it's not efficient, you don't need to worry about it. Just write software on an existing processor and be done with it, right? And for a lot of things in the real world, that's fine, right? If you have something that has operates on a human time scale, you have a processor in a gigahertz range, you can do a lot of things with that processor. You don't need to worry about, actually making specialized hardware. Okay, but assuming you have an application scenario where you really do care for efficiency, what can we do? Well, we need to optimize. And before you optimize anything, you should always have metrics, right? And so for hardware, most classic metrics are PPA, which is short for power, performance, and area. And they all have their own concerns, right? Of course, power, I think we're very familiar with this in terms of how it affects battery life and mobile device sizes. It also, of course, has impacts with regards to, if you have a power bill for a large data center, but it has a lot of other ways to kind of manifest, right? For example, if you have a box you plug into the wall, making it take less power doesn't just save you money on your monthly power bill. You can also save money on your power infrastructure, right? So building a large data center, a non-trivial portion of the cost isn't just the hardware, it's actually the hardware supply that power at that level, right? So if you can buy with less power, you also can get by with less that kind of stuff, right? The cheap performance, of course, obviously you want to go how fast you can get through things. And then area, which is our proxy for cost, right? Which is, in a chip, it's how big is the chip, and that's kind of, determines the cost. And the reason why, of course, is that when you manufacture chips, they're usually made, entire wafer at a time with many dies on it. And the cost to process the wafer is usually roughly constant. So thus, for a given amount of constant cost to make the wafer, if your chip is really small, you can have many chips within that wafer. the amortized price is really low. If it's just really big, then you get less, and you get less, a greater amortized price, right? So area is kind of that thing. Meanwhile, for doing a FPGA application, um, how big or small your design is determines how big or small FPGA you can get by with your application. And that's also going to impact cost, right? If you buy a bigger or smaller FPGA, it's going to have different price points. So at the end of the day, the most common metrics are PPA. Cool. So these are all very low level metrics. What other metrics might you analyze for a design? Yeah, good. Oh, great metric. Okay, what about cost to develop or time to develop? Good metric. Yeah, that's a good one. What else? I'll elaborate on this for a second. I mean, that's definitely in the spirit of the agile philosophy, right? Where we're trying to get a win in development time. So if our development process can take longer, well, that's not very agile of us, right? uh, what else might matter for a chip? Go ahead. Usability. How could you define that? Yeah, so usability, how well can someone just use it in their applications? Yeah, so if you're trying to make some sort of SoC, others could integrate into their designs. How well does that match, likely usage scenarios? Good. Go ahead. Cost for verification is another good one, right? So, um, yeah, it's a great one, right? So imagine you don't just want a chip, you want a chip that does the right thing and you're confident does the right thing, and there's some amount of cost to verify that and get to that point. Now, so I'm glad to bring all these metrics up because there's actually are a lot of things to consider. This is only a very myopic view of a small portion of it, right? This is focusing on once the chip exists and you believe it does the right thing, you've verified it, and you've paid the development costs, and it has the right usable features, then you have these metrics, right? There's a lot of other metrics that are kind of higher level, and the reason why they aren't in this slide, not because they aren't important, is because they're higher level. So things like the engineering cost in terms of how long it takes to make it, verified, et cetera. But there's also architectural little things, such as what does it provide? In the modern era, also we care a lot about security, right? So you imagine a lot of these things which are also important, but they're more architecture level rather than physical design level. But yes, these are important things. Great, great suggestions, folks. Okay, let's keep moving. So if we are going to optimize, like I said, you need to have metrics, right? You can't just say, I'm going to optimize my design. Well, optimize it for what, right? Especially if you're doing PPA, that's three different metrics, right? So you kind of have a choice, right? So what's the typical process? Well, first of all, you need to pick what you're targeting, right? You can't just usually optimize your design abstractly in space, right? You have to have some sort of very concrete target. Okay, I'm optimizing my particular design for a particular implementation technology, whether it be ASIC or FPGA, and even more specifically, I want to optimize it for, let's say, TSMC 10 nanometer. I want to optimize it, or maybe I want to optimize it for a particular, Xilinx FPGA or something, right? And so once you have a kind of technology picked out, it starts making some of these other things more clear. Before you jump into this, like anything when you're optimizing, it's also true in software. You should measure first. That way you kind of know what you're getting yourself into and what's possible. And you should kind of try to ballpark what's possible, right? If you see, oh wait, I'm doing pretty well and it's hard to imagine doing better, well, maybe it's not worth me investing heavily, right? Um, for example, for me, thinking at a much higher level, people also say, oh, it's still specialized hardware. I would love to build specialized hardware. That's kind of what I'm all excited about as an architect. But what's a good baseline? Well, for some applications, a good baseline is a GPU, right? And guess what? If a GPU is doing a good job with your workload, by a good job, I mean it's keeping its memory bandwidth and its ALUs largely occupied, doing useful work, it's gonna be hard to beat, right? Because you could build a chip. Are you build a chip with more ALUs than NVIDIA? Maybe, maybe not, probably not. Are you build a chip with more memory bandwidth than NVIDIA? Probably not, right? So if that GPU is actually fully, crunching and you're trying to build a big chip, it's hard to win. Now maybe you aren't trying to build a big chip. Maybe you're trying to build a small chip. You want to, make it super, super, super energy efficient and super, super cheap for NVIDIA. That might be possible. So it very much depends on what your metrics are. Try to kind of identify an opportunity and then ballpark it, right? You know, what best case scenario, if everything I hope to have happens, what happens? If the answer is nothing, then why are you doing this, right? Hopefully there's some kind of benefit. And now, of course, we are going to talk about this in this course is that we've been talking a lot about generators, right? And with generators, it makes it easy for us to try other alternatives, right? So we can think a lot about, oh, well, let's um, change it in this way, and now we can easily consider an alternative design, right? Which might be more efficient under certain conditions. And so this is kind of getting more to the point of why we're doing all this stuff in this course is that if you're writing one-off code in Verilog, even if you heavily verified it, if you decide to change your architecture to try and accelerate it, you got to redo a lot of the coding, redo a lot of the verification. If we're lucky, not guaranteed, but if we're lucky with a generator, we can change it in some ways that perhaps won't be able to verify it and might actually be more efficient, right? And that's kind of the point. Hopefully, if you have a generator that's more portable and more reusable, as we discussed, than a single design instance, right? But no matter what you're doing, after you pick technology, you've measured it, identified how much you can improve it, at the end of the day, you're going to try and make trade-offs, right? You're going to try and sacrifice one metric to improve another metric, right? I'm going to try and make my design less performance than GPU, but hopefully more energy efficient, right? Um, and the reason why you have trade-offs, of course, is that's what it takes to be competitive. If you're able to improve all three metrics at the same time, that was not a very good design, right? That was a design that just wasn't very good. Usually improving costs something. There's some sort of catch or some sort of price. And so that's what we want to be, kind of making those trade-offs. Cool. Questions so far? Okay. And so I think this year our class skews a little more E than average, but let's kind of appreciate for a moment at a high level my caricatures of the two types of design, right? So in the easy world of software development, we spend a lot of time thinking about what our code should do. When it comes time to optimize it, usually it's just performance. Oh yeah, how long does it take? And if I make my code run faster, usually that runs as faster on this CPU as well as another CPU. And the reason why, of course, is AMD versus Intel. Yes, they're different, but from the code point of view, are they that different? Maybe not, right? And the other nice thing, of course, is that the compilers are pretty automated, right? You can use whatever build tool you're using, the compilers, and it does most of it on its own. You don't spend a lot of time telling what optimizations to run. You say just O2 or O3, and it does the rest. And it's also going to give you the right result, right? As a longtime HPC programmer, if a compiler ever gives me incorrect program, it's dead to me, right? Like you had your one chance, you don't get two chances, right? And so actually, I technically gave ICC three chances, right? And so I'm done with it, right? ICC is dead to me because yeah, I've got an incorrect assembly of ICC, and I don't want to get anywhere near that thing, right? Like someone ships a compiler and gives me incorrect code, no, I'm not gonna touch that. That's software. Uh, and like I said, what's interesting, for example, is we're only targeting one metric, performance, right? Actually, if you're programming 30 years ago, you'd be really worried about memory usage. Actually, it's a huge problem, right? Like programs in the data were competing for memory in the machine. And 30 years ago, you have an order of megabytes in the computer. It's actually a real problem. Making program code fit in there as well as your data. So they're working really hard to shrink the code, for example. And so now we don't worry about that. Now it's only performance. Life is pretty easy. Meanwhile, you go to the hardware world, it gets a lot harder, right? So what happens? Well, um, it's not just about implementing design. You need to make the physical design. You need to optimize it. You need to verify it. These are all big steps for a lot of people often. And it's not just one metric. There's three metrics. As I said, there's trade-offs, right? There's these power performance areas. There's trade-offs somewhere in there. And they're often very technology dependent, right? Targeting a certain ASIC process, a certain FPGA or something. Those are going to have certain impacts. And then the thing I think is the most surprising people to kind of are new to hardware design is how annoying it is to work with these tools, right? These tools are not highly automated. They require significant human intervention and oversight, right? In other words, you put it off on your design, it might spit out incorrect stuff. So you have other tools to try and verify that to make sure the first tool is not wrong, right? You often have to do a lot of work to make what they call a tool flow, which is you using your own scripts to stitch together multiple tools to kind of make the entire process. When we're writing software, we take it for granted. If I'm running GCC, that GCC actually does, the compilation and the assembling and the linking all in one tool, and the loading, and we don't really think about these separate steps. That's kind of all continuous. With hardware, no. We need to build a flow and kind of do every step manually and kind of connect things together. So it's a lot more work. It may not always be this way. People often ask, why is it this way? Well, part of the reason why it is that way is because there's not a lot of incentive to be otherwise, right? Where most hardware design tools are commercial products you pay money for. And so if you're paying money for the software and you're paying money for the software because they're also paying a lot of money to build the chips themselves, you're willing to overlook these weaknesses because you're already paying people to do this thing. You're already paying licensing fees, you're already paying the manufacturer a chip. In fact, the software is really hard to use, isn't really a killer to you. However, if you're instead of doing a big, large corporate chip, you're doing a small project on your own, this pain is really real, right? And it's really a problem. And so people are trying to fix this. There's a lot of open source tools. This course, of course, benefits from them. And we're also trying to make the tools less grouchy, right? We're working on it. It's not there, but we're getting there. It's getting better. Cool. Okay, so This goes back to the slide we had very earlier in the quarter. And now that we've actually been doing work for a while, we can actually, of course, appreciate this in more detail, right? We've talked about contrasting a waterfall approach where you do all of one step completely before moving on to the next steps. You're going to fully specify your design. You're going to fully implement each block individually. You're going to fully test each block individually. Then you're going to integrate all the blocks. Then you're going to optimize the blocks. And so one of the challenges of this approach is that let's say you integrate it all together and you look at the end overall result in terms of, one of your PPA metrics, performance, power, area, and you find out, oh my gosh, I missed the target, right? I'm like way bigger than I thought it would be, or it's way slower than I thought it would be, or way more power than I thought it would be. Shoot, then you got to go back and do stuff over here, right? And so you could say, oh yes, I need to go into the optimization phase, but at that point, maybe too late, right? And you need to kind of spend a lot of time redoing these stages, right? So the intuition, of course, is that you can't possibly know the right design in the beginning. How could you know it before you did it? So you might as well take a more iterative, agile approach. And that is, you design something, implement it, optimize it, verify it, and then, see how close you are, right? And go through soup enough times, eventually start figuring it out. And for a lot of projects, you might find the more times you're able to go around this loop, the better and better your design can be with regards to efficiency, right? Where it's really hard to know in advance sometimes what particular architecture is going to work really well in a given implementation technology, right? It's hard to know in advance. Um, but if you build a mock-up of the architecture and actually push it through the tool and see how it goes, you realize, oh wait, this is not working well. Okay, we'll try this other one. And so you can kind of quickly try more things. And so in the case of physical design, yeah, we really want this agile process going. We really want to get the tools running our design early and get feedback early in terms of the physical costs. That way we know what to optimize. If you've ever been in a tape-out project, whether it be academic or industrial, sometimes you hear expressions like an RTL freeze, meaning that, at that point, in other words, they're saying you have finished the implementation phase and the physical design team now wants you to give them RTL that you're not going to change, and they're going to go ahead and physically optimize and manually touch that. Well, guess what? The reason why they're telling you your RTL is frozen, you can't change it anymore, is because they're manually doing stuff, right? They don't want to do it over again if you change your mind. But that's a disaster. It means basically you only get one shot. And how's your one shot going to be right? It's not going to be right, right? And so you need to automate everything so that way you don't flinch about doing this over and over again, right? So if you can go from chisel and it's automated to get pushed into Verilog, to get pushed into your various design tools, and get pushed through your entire flow, run your verification suite. If this is all automated, you don't mind writing this over and over again, right? And heck, this might be a lot of compute, but you know what? Put computers to work. Make tools do the work. That's one of the themes in this course, right? So automation can help you there. Cool. Questions? Yes. Oh, great question. The question, of course, is, wait, how is Agile able to be agile and iterative when the physical design team need to make manual changes? And my answer is, that's the thing you got to stop. Stop the physical designers who want to do manual changes. Like, no, chop the hand. No, bad. Spray water on like a cat. I don't know. That's where you got to get involved, right? Like, you've been in these academic tape outs. That's what they want, and you can't let them do that, right? Because it's not scalable, right? We've all done this. You take a design, you push it through a tool flow. You didn't do anything weird, and you have a D or C violation, right? Somehow your design is unmanufacturable because the tools didn't follow their own freaking rules, right? When you have that scenario, you need to use scripts to fix that. You do not let a human touch it. Because like I said, the scenario described. Now you're absolutely right. If you're using Chisel and you have a physical design team that wants to take your design and freeze it and then manually optimize it, and they don't want you to change it because they don't want to manually re-optimize it, then you're not agile. Then you're waterfall. You're absolutely right. So Chisel doesn't mean you're agile, right? Being able to run through the entire loop, largely automated, unencumbered, that's the agile, right? That's the key thing. So in this course, for the most part, we don't have back end. We're mostly all front end. So you don't really get fully lived at. But today we're kind of talking about that, about what that might be like. Yeah. You mean like, yeah, yeah, this can happen. This is something that my colleagues did in grad school. Um, and this is kind of, a dream put forward by the government research funding. So CHIS, of course, is the recipient of many years of government funding. Yeah, this has been done. So the kind of dream was, okay, what if I had a design, go from a RTL level design to a working GDS with pretty high confidence and have that be automated in a reasonable sense. They made some progress on that. You may have heard something called the Open Road Project, which is now a newer Dropper program that's also trying to make this less human intervention, more automated. It's not all the way there. But Open Road's, dream was, okay, given this design, could you have working GDS in less than a day? That was kind of their metric. So a day is pretty long. But they're also, doing the full physical design, not just a lightweight RTL testing kind of stuff. But in terms of how this plays out, I mean, this is the competitive advantage of a company like Sci5, where Sci5, those people, when they were in grad school, they made 40 bucks a year. Like, how do you do 40 bucks a year as a student? And the reason why is it's automated. Otherwise, you have no chance. And so they can do 14 bucks a year, and so they got really good at making chips. And then Sci-Fi's competitive advantage, everyone isn't they know RISC-V better. Their competitive advantage is they can spin up a chip faster than anyone else can and cheaper than anyone else can because it's largely automated. And everything that's not automated becomes a bottleneck. So one of my good buddies was telling me one of the most hilarious problems they had is they had a really automated flow editor chisel. You could put things down SSC and it would get run through the entire tool flow, it would get laid out, whatever. But then some poor engineer had to look at the design and write documentation to ship it to a customer. And so they had to automate the documentation generation. Or like they had they text segments they start stitching together. So that way you get a 200-page PDF that tells you, oh yes, your bootloader is at this address, this IO device is at this address, and it kind of generates all that for you automatically. Because it's not automated, it becomes the bottleneck. So kind of the dream of this whole thing is embrace automation, right? Whenever possible. Now, as discussed, not all tools are friendly to this. Not all tools are amenable to this. It's not as easy as just, import a couple of Verilog files and boom, you have a perfect ready to go chip for tape out nowadays. That's what we dream for Open Road, but we aren't there yet. But this is definitely an aspirational slide of, let's get it more automated, more iterative, get more feedback. And even if it's not perfect, for example, let's say you have a ASIC design and you push this through a flow, and because you aren't there manually fixing it, you have DRC errors, right? Those are things, it's going to say you can't actually make the chip. Even those DRC errors, if you fix them, how much is that going to change performance? There's only a couple small DRC errors. It's not going to performance very much, right? And so you still learn something from running through a flow in spite of those DRC errors. Oh yeah, my design is looking at something like 1.2 gigahertz. Is that good enough? Yes or no, right? And then you kind of get a feel for it. And so I said, you're right. This is kind of maybe you give me some wonderful criticism, which is well deserved. Yeah, I think you're right. Maybe this is perhaps a caricature of two extremes, right? And we would love to be far to the right in this agile world. We aren't quite there yet, but we're going to aspire to get closer to that. More agile, more iterative, more automated, kind of the goal. Cool. So between this talk and some other talks, you may have heard me kind of mentioning a few different aspects of chip design. This is a one-slide summary of what a typical tool flow might look like. It's usually much more complicated, but at a high level, the main things that need to happen is somebody take your RTL, let's say it's Verilog, maybe it came out from your chisel, and your chip design comes out the other end. So what are the main things that need to happen? Well, you need to turn that Verilog into actual hardware components, various logic gates and adders, registers, whatever. That's synthesis. Of course, these aren't just random logic gates. These are logic gates or components inside of whatever implementation technology you're targeting, perhaps a certain ASIC flow or perhaps a certain FPGA. And you place those things out in 2 dimensions, perhaps soon in 3 dimensions, but for now, 2D. Lay those things out. And then at some point, you need to wire them all together. And now, at a high level, this is like what you need to do to make it as a chip that functionally works, right? That works in theory functionally, right? Now, of course, there's a lot more details. We mentioned there's some of these things I kind of have only these initials for. But after you get to this design, you want to make sure it's correct, and there's certain things you do. For example, you might do something called a DRC, or design rules check. Basically, even though you're using all these tools along the way, and it should hopefully be automated, this design may actually be unbuildable, right? And so there's a DRC program that checks your design for certain criteria, and if it doesn't meet those criteria, it's unbuildable, right? Or you may also have something called LVS, or layout versus schematic. Basically says, even though you have a wired up chip design over here, if there's a bug in one of these tools upstream, this chip may actually not correspond to this RTL. That's a problem. And so you have a lot of these tools in the real practice that are constantly verifying and checking things, and it's not perfect. You kind of have to be paranoid and verify more and more and more. But at a high level, I just want people to aware of the kind of major steps. There's kind of synthesis, which is taking your design and figuring out what components it's going to be, putting those down somewhere in hardware, and then wiring them up together. Now, in practice, this is like a linear flow like this. This is 1980s style chip design. In the last few decades, it's got a lot more complicated. Very often, you will go through all this, and then the tools will realize, oh wait, we didn't make timing, and if something out of fashion, it's going to go ahead and try and improve it. So you know what? They find the critical path. This is the slow route. We'll go ahead and maybe synthesize that with some faster components. Maybe place those closer to each other and rewire it, and maybe fix that critical path, right? So a lot of times, the casuals themselves actually run these operations intermix and repeat certain less steps over time. But at a high level, it's people to be kind of aware of these steps. Cool. Questions? Okay. Okay, so that's kind of the end of the brief lightning whirlwind tour of kind of physical design optimization, so you're aware of it. We're going to shift gears and talk about memory. But any questions on physical design first? Okay, let's go talk about memory for a second. So why are we worried about memory? Memory is one of those things where for most designs, you're going to need some sort of memory. And it's actually a significant cost contributor, right? So if you're building some sort of actual electronic device, often memory is actually has a significant impact on price. The memory itself is some amount of price. The interface of the memory is some amount of price, and it kind of all adds up. For example, my own research group, when we have our our servers, usually the DRAM is a 40% of the price of the server compared to the rest, right? This is a significant portion, right? Um, Now, if you're building a chip itself, often you might want to have SRAM on there, so on-chip memory. And you look at the processor chip, often approximately half of the chip area is SRAM. So once again, major cost contributor. So how you use memory is really important because it doesn't really impact your cost. Now, that's just cost. If we go through our various PPA metrics, right? So we talked about, so cost of A, right, area. What about P for performance? Yeah, it's also a real problem, right? Where depending on the workload, you could be memory limited, right? It could be memory latency or memory bandwidth. Those are both could be issues for you. And you can be holding back the performance of your design. Now, why would you even deal with memory? Well, there's a few different reasons. Number one, you often need to hold the data just to have one copy of it somewhere. But you also need to have memory to hold intermediate values. And what's kind of fun, the more you kind of play with writing hardware designs, writing programs that make hardware designs like generators, and you kind of go back and forth, you get a real appreciation for data flow, of how data flows between operations and a computation. The thing that comes out of that is if you know exactly who's producing data, oh yes, this ad's producing a value, and it's going to be used by the multiplication in the next step. It's a very clear data flow, right? You can do that. Now, there's some scenarios when you're writing an algorithm, it's not clear who the producer or consumer are, right? You can imagine, maybe think of more like your classic mutable C program, where you're actually using memory, and part of using memory is the program itself is computing which values to read. And so perhaps another way to think of memory, it's kind of like an all-purpose connector or a network, right? And it's kind of like a way to communicate between operations rather than through space, like a network would be, but through time, right? So you can do an instruction now, and then some number of cycles later, you can read that value and operate on it. And the thing is, you want to necessarily know the producer and consumer instructions may not know about each other time they operate, right? So this is why you have this memory. And so it's a little bit more philosophical about architecture for a second, but suffice to say, you're gonna need memory. It's expensive. You're not careful with it, and it's also going to limit performance. This is why we care about it. Yes. Can I plug over RAM? Yes. So let's say here we are at open source world. We want to have SRAM in our design. Well, guess what? The best and really only tool available for that is OpenRAM. And so you can use that, of course. Be happy to. So yeah, that's what the A is for, right? That's the rapid agile memory, right? Okay. Um, so speaking of memory, I've decided to kind of make sure we're on the same page when we talk about the terminology. So how big your memory is, of course, that's the capacity. Depending on the units, it might be in terms of words, might be in terms of bytes, might be bits, but yeah, how much space does it have? There's some amount of latency to access it. If you look at how much data you can transfer over a unit of time, like your rate, that's of course your bandwidth. Now, when you access the memory, you usually put down in the form of a request. Hey, I want to read this location, or hey, I want to write this location. That's the request, and then you get that data through some sort of access width, however much wide it is, right? So if you're reading, you get some amount of access width data back. If you're writing, you send some amount of data into it, right? Um, Now, memories, these are special structures, and so usually we have specific ports, right? So I have a port that's a read port, or a port that's a write port, or maybe have even a read/write port. Those are all possible. And one thing you might hear me as architect talk a lot about is getting multiple memory requests in flight at the same time. That's a way to get more bandwidth, more parallelism. Cool. Questions on memory terms? Yeah, the question is, how do you use Chiseled in another memory project? For example, something like OpenRAM, as previously mentioned. I'll get to that in a few slides. And if I don't, remind me. Basically, we're going to cover a few architectural level optimizations, and then I'll conclude with some practical advice for Chisel and Esther where that comes in. Actually, maybe I can, no, I'll come back to that. That sounds better. Cool. Okay. So if you're taking an architecture class with me, I'm obsessed with this one law, and I want to keep that tradition going. So what is Little's law? It's a queuing theory result. It's really simple, right? If I have some sort of, queue, or you think of, in this case, maybe a memory pipe, memory port, some amount of throughput, some amount of latency, um, they're actually all related, right? In the sense that how much stuff is in flight is really just the product of how much bandwidth you have times the latency. So sometimes you might hear it even referred to as, bandwidth latency product. But why does this matter? Let's say, for example, you are trying to improve your memory performance. And so, well, despite your best efforts, the memory can't change its latency. And so in order to get more throughput, you need to have more parallelism, right? And more requests on flight is a classic result, right? But they're all related, right? Let's say you're able to somehow have the latency of your memory. Well, if you have the latency, I'm saying over requests in flight, that means you have twice the bandwidth, right? So it's going to help you relate things. And so, for example, some of the things we're going to see today, we're talking about changing parallelism or changing some of these other metrics. You can see how they kind of relate. Cool. Questions on Little's law? Okay. So when it comes to actually trying to decide how you're going to design a system with memory, you kind of want to get away with the cheapest memory you can. That's kind of the goal, right? Obviously, there's always really nice memory, but it's often really expensive, takes a lot of power, has various costs. So you want to kind of get by with the slowest, cheapest memory you can, often points, right? And so in practice, what are main pain points for memory? Usually, it's latency is too high. Because we're well familiar from architecture class, that DRAM might take 50 nanoseconds to access, and your processors running at 4 gigahertz, i.e., 250 picoseconds per cycle. There's a mismatch there. That's a problem. Another problem that comes up is a lot of times you have a lot of components that want to access the same memory. And each component wants its own memory port, and you end up requesting way too many ports. In practice, a lot of memories can only support 1 or 2 ports, right? SRAM can support 2 or more sometimes, but DRAM usually only 1 port per component, right? And so there's kind of a port limitation. And in some extreme cases, someone's just trying to move too much bandwidth, right? Now, in 2023, when we have things like HBM, there's a lot of bandwidth available. Not many designs can drive more bandwidth than that provides, but some people can, in which case they want even more bandwidth, right? And so how does Arctic come solve this? Well, we rearrange our system to try to reduce the bandwidth demands, reduce the capacity demands, tolerate higher latency, get by with a cheaper, slower technology if we can. So these are various things we can do. And so as a reminder, for technologies, right, the best thing we know of are registers. Of course, we have SRAM, on-chip memory. DRAM is one kind of off-chip memory. In terms of other off-chip memories, we have things like phase change memory, PCM, or flash, right? But this course is really focused on just these left two, right? SRAM and registers are the kind of things we're talking about. Okay, so talk about one intervention, banking, right? So the problem is that somebody, the way they've specified their thing says, I need this much bandwidth for memory. And despite your best efforts, if you're working with a tool like OpenRAM, OpenRAM tells you, I can only give you this much bandwidth, right? So how do you close that gap? Well, banking is a way to put together multiple memories to provide that bandwidth, right? Now, in terms of how it looks the outside, they see a memory, right? But internal inside memory, you have multiple banks. These are each smaller memories, and they're all somewhat connected together and exposed as more things. So a very common situation might occur if somebody wants a lot more memory ports than the fundamental memory technology allows. Maybe memory technology only allows for 1 or 2 ports, and they want, let's say, like 6 ports. Well, it's hard to do, right? But if you have a lot of banks, you can do it, right? So it kind of depends. Cool. Okay, so next you go ahead about banking. You have 2 choices. Depending on the scenario, you have choices, right? So one option is, hey, you can take the memory you're supposed to be providing and put 1 over n of that on each bank, in which case, as long as their accesses are sufficiently dispersed, you get by fine, just fine. Alternatively, maybe you can't guarantee that, in which case each memory actually holds redundant data, and you keep reading it all, right? So for example, let's say you want a lot of read ports, you don't care about having very many write ports. Well, one way to get that accomplished is to give every memory a read port, so I would have like lots of read ports and lots of memories, and then They all share the same write port, so that way when someone writes it, it goes to all the copies at once. They're not inconsistent. That's kind of an extreme example, but this comes up, right? Let's say you're building a processor and you want to have, a big out of order core. I mean, you want to be 8 wide or 12 wide or something like that. You're going to need, 12 ports in the register file. And guess what? They can build these. But banking is a big part of how they can do that. Cool. Okay. So yeah, this says the banking is a lot more artificial details can go into, but this is kind of a high level point, right? That is, you can have multiple memories working together to give the illusion of a bigger memory of somehow that has usually more bandwidth is kind of the goal. Okay, another invention. This is one that's actually a really common engineering case. The memory is just one example. I call it smoothing out demand, right? Which is very often when we engineer something, we have some resource we can provision, and then there's some demand, right? And demand is not constant, right? At times it can be high demand, at times it can be low demand. A really good example is like a road or even a highway. If you go on, Highway 1 at the wrong time of day, we're all familiar with how trafficy that place can be. Very trafficy, very slow. You're probably sitting there going, oh man, I wish I'd make this highway wider. If you go there at 3:30 a.m., you might not see any cars, right? You might even walk out on the freeway and become liable to become roadkill, right? I mean, that's kind of the point. And so if you take the average number of cars that get through Highway 1 over a day and divide it by a number of hours in a day, the cars per hour may not be very high. So you might say, oh yes, 2 lanes is perfectly appropriate per direction. But the reason why is people don't travel in a perfectly uniform manner. They kind of do very bursty. They have, rush hour or whatever else they're doing. And so that bursty demand can cause problems. And so the issue is, as an engineer, if you have a very bursty demand, you have a choice. Do you provide enough resources to handle the peak, or do you provide enough resources to handle the average? And depending on the scenario and the resources available, you kind of have a choice, right? If you handle the peak, that basically guarantees you're going to be idle a lot of time. You're not at peak, and it's just very wasteful. Now, providing enough resources for the average, that means whenever there is a peak, the line gets very long. So for example, if you're flown recently, waiting for airports to do a TSA, they actually are guilty of provisioning pretty close to the average. So for example, if you get there, let's say 4 or 5 a.m. in the morning, if you go fly for a flight, they actually don't have enough people working there, but they know they'll catch up. And so they get, like a line starts right away first thing in the morning. And then they know that, by 10, 11 a.m., the morning round of flights are done. They'll start shrinking the line. And so they made a certain choice in that trade-off, right? As an architect or an engineer, right, our goal is that peak and the average both be the same, right? If you have a peak and average that are very similar in their demand, life is good. If you have a huge gap between a peak and the average, then you have a choice between, do I support the peak and then be wasted a lot of time, or do I support the average and wait a lot of time? You kind of just trade off, right? And so the idea, of course, would be, what can I do architecturally to try to smooth out my traffic, right? Somehow make my peak and average be very similar, in which case I can survive, size for the average, and it's not too bad for the peak, or vice versa. So when it comes to doing that, there's a few different ways we can do that, but at a high level, the kind of goal is to, as the name implies, smooth out the traffic, right? So things you might do are things like pipelining, where you basically, another way of saying queuing, right? You're trying to spread it out. And double buffering is a very particular type of queuing we'll talk about in the future slide. But any questions so far? Okay, so when it comes to trying to smooth things out, one other option you might have is trying to overlap communication and computation. It's another artificial trick that comes up a lot. So sometimes you can imagine your component, maybe your state machine is, oh yes, I'm in the reading state, or I'm in the computing state. So you very explicitly are in compute or memory transfer mode. But the truth is that if you're doing, when it comes down to the hardware, you actually tend to have compute hardware and memory hardware, right? So if you're doing only compute or only memory, only communication, that means one of them is idle, right? That's the case on the left. And so ideally, you can somehow find a way to overlap the two to get reduction in execution time. Now, there's always a lot of caveats, right? Now, of course, for example, if this communication over here requires result of this computation, well, we can't really overlap those because it requires that result, right? There's a dependence there. Another interesting caveat is if you're doing computation communication overlap, the best improvement you can get is 2x. You may think, wait, I can do better than 2x? Yeah, no, you can't, because one of these resources is still going to become the limit, whether it be, in this case, communication is still the limit, or maybe it's computation. But the point is that if they're both utilized exactly the same, if you do one or the other, then you overlap them, that's a 2x speed up. If one was used more than the other one, let's say one's used 75% of the time, then your improvement is actually much less because you only can basically get that 25% time back by overlapping. And so like I said, computation communication overlap's a great trick, but there's a limit to it, right? And in order to have this, sometimes with overlap things, you need an algorithm or application that lets you overlap communication, right? Sometimes, like I said, if you communicate data to then compute on and spit it back out, you can't do communication if the data is not available. If the data is not available, so you need some way to have this communication be dependent on not this computation, right? But at a high level, what are we doing? It is actually kind of a form of pipelining. It's a form of taking advantage of parallelism, exploiting that temporally. Okay, maybe we'll be quiet and pause for a second and let people kind of ask questions or whatnot. Okay, another intervention you might have, mentioned this 2 slides ago, was double buffering, right? So double buffering, uh, the issue is we want to efficiently overlap computation and communication, but we may not have enough memory bandwidth to do this, right? Well, we learned about banking earlier. This is kind of a fun combination of the two, right? Basically, we're going to say is, hey, I'm going to have 2 copies of my memory. I'm going to compute out of one and communicate with the other one. So you can see, for example, in this first phase, yeah, computes out of memory 1, communications out of memory 2. Then in the other phase, I can communicate out of one memory and compute in the other memory. So basically, what the other words is saying is, if I have some sort of application where I can somehow divide my memory for computation into 2 different units, right? I have element 1, element 2. I can be computing on element 1 while I'm transferring element 2. And then when I'm done computing element 1, I can start computing element 2 and I start transferring the other one, right? And so the buffer is just a way of kind of having the hardware all working in parallel that way, right? We have one hardware is doing a transfer versus one is doing the compute, and you can kind of swap which one's which, right? So you have 2 memories, right? These are the 2 buffers, so to speak. And so in this case, this one's computing versus this one's communicating versus now you swap roles. And they're going to swap back, and then they swap back this way, then they swap back that way. And so you kind of go back and forth each time they finish. Cool. Questions? So these are all kind of high-level architectural tricks. And so when you start designing components, you're trying to optimize them, these are some kind of tricks to have in your back pocket to be ready to improve things. These are more architectural rather than physical design, some of these, but I'm still kind of there. Okay. So now back to the question from earlier. I'm going to go ahead and instantiate memories, how we go about doing this, right? When you design a system, typically if you have object memory, you really know why you have object memory, right? You don't just kind of do that casually. Because there's a significant cost that comes with it in terms of having those wires, those pins, the other components in your board, whatever you're doing. So you don't kind of do that very nonchalantly. Usually it's a very deliberate choice, right? You know that I need a certain capacity and I can't get that otherwise. Or I actually want a certain price target and I can't get that otherwise. So you know why you're doing that. So assuming object memory, you know why you're doing it and you kind of have a plan, we're going to instead focus on on-chip memory, right? And so, well, if you're doing an ASIC, your choices are, of course, registers or SRAM. Now, SRAM, usually you're not going to just make yourself. Usually you either come and provide to you by a technology library from the foundry and a handful of pre-made sizes, or if a handy memory compiler like OpenRAM, and you can go ahead and make your own memory, right? And so the result of this is that you don't just get memory, right? You need to say, you know what, I want memory with these dimensions, and you deliberately instantiate it, right? So it's kind of a very clear, very deliberate choice. And you know, if you're really doing a good job designing, you're gonna say, you know what, I made OpenRAM at this dimensions. Let's make the OpenRAM in different dimensions, and then bank it and see if I get a better overall result. You can kind of see there's a little bit of design space to explore there. Where if I want to get a certain bandwidth, okay, well, you can imagine a very simple experiment. Use a memory compiler, make a 1-port SRAM. Okay. Now make a 2-port SRAM. Okay. Compare the performance to the 2-port SRAM to 2 1-port SRAMs working in a banked configuration. See how that compares in terms of PPA. And depending on technology and the trade-off, you might be surprised which one is the better one, right? It's not clear from the outside which one's going to be more efficient, right? It's not guaranteed. So that's kind of that scenario. When it comes to an FPGA, you have a lot more choices of memory. It's actually a little bit more richer design space. You have registers, you have LUT RAM, you have B RAM, and some Xilinx parts, you have Ultra RAM, right? What's interesting about that, despite the variety of memories, I'm a big proponent of not intentionally instantiating them. People are like, what do you mean? I'm like, I mean, write the Verilog in the right way. Let those tools infer the fact you use that memory, and they'll know better than you, right? For example, on an FPGA, there's certain trade-offs between LUT RAM, VRAM, and URAM, namely in terms of capacity and bandwidth and other terms of types of trade-offs. And so you actually shouldn't be manually instantiating those RAM. The tools should be looking at how you're using memories and making the right choice. And so if Verilog's written the right way, the tools actually will correctly infer this. I spent some amount of time in Chisel previously making the chisel Verilog of memories such that popular FPGA tools would infer BRAMs automatically. Is it guaranteed? No, but it makes it more likely, and I'd rather people do that than trying to manually use macros to get a BRAM for sure. Once again, kind of in the spirit of make the tools do the work. Like I said, use a human on a large FPGA design. Sometimes an optimization choice between, okay, well, I have a lot of memories in my design. I should maybe use BRAM. Okay, but actually, if there's space available, maybe using LUT-RAMs faster. And if there's less available, you should use them, right? And so that decision, that trade-off, the optimization, that's hard for humans to know, but maybe the tools know that. I was like, okay, they can figure out, oh, wait, this logic's close to these BRAMs. I should use these BRAMs. The other BRAMs are far away. And so instead of using BRAMs, I should use LUT-RAM and be close, right? These are the kind of things that tools can explore a lot better, a lot faster than you can as a human. So it's better to let them do that. Now, with regards to Chisel, what does Chisel provide? Chisel just is basically a high-level functional specification, right? It says, hey, I have memory, and you can basically say how many ports it has, how big it is, the data type, of course, and basically how many cycles it takes to access it. And so if you're doing things like FPGAs, yeah, you can basically, if you use a mem, you're gonna get registers. If you use a sync read mem, you're probably gonna get BRAMs if you have 2 or less ports. If you have like 5 ports, you're not gonna get BRAM. Meanwhile, for SRAM, when the SRAM, of course, means you're gonna be using an ASIC, you actually need to be more deliberate. You can't just let the tools do it. You're gonna need to say, hey, this memory is gonna be an SRAM, so you gotta go dig into your ASIC library and figure out, okay, am I using a preset Foundry component and you're stitching them together at the right size? Maybe your Foundry only gives you a SRAM mat that, let's say is a kilobit, and you're like, okay, well, I want 8 kilobits, so you put 8 of them together myself. Or memory compiler, same kind of thing. So you got to manually run that. When it comes to Chisel, you actually can use a command line flag called externalize mems that will generate stub functions, so it's easy for you to kind of go ahead and use another tool. So it's going to generate the Verilog, rather than instantiate the memory, essentially it's a module, like a black box, that can be replaced by the memory, and then depending on what version of Chisel you're using, actually gives you a JSON file, which you can feed in some other tool to actually get the memory you want. Okay, so I told you, here's the memory module. You need to make a Verilog file that has that memory module, and then here's the parameters it has. Okay, it needs to be this many ports, this latency, this capacity, etc. That little detail we're probably not going to do in this course. So those of you who are worried about that, no, you're not going to do that. You're mostly going to continue to do front-end only kind of stuff this course, especially for your projects, but just so folks are aware of what's kind of out there, what's possible. And of course, we talked about in Chisel, we're going to talk about doing read ports, write ports, or even read-write ports. You can do all that. I would say the most common mistake people have when they try to get BRAMs out of a Chisel memory, it doesn't happen. First of all, it needs to be a sync read memory, not just a mem. But limit the number of ports, right? If you have like 4 ports, it's not going to work. You only have up to 2 ports, right? So that's the limit for BRAMs in the hardware. And so make sure you perhaps use muxes, whatever you need to do to make sure that if you have a lot of people who want to access that memory, they arbitrate first, and the actual requests come in only through 2 ports of that memory. And that's one way to kind of guarantee you get BRAMs on FPGA. Cool, question. Well, great. So yeah, so when we're talking about memories like that, those are all sync read mems. So like a regular mem in Chisel, because it has 0 latency in terms of cycles to access it, that's usually going to be registers in most technologies. You can't really get that in SRAM. There are people who can do SRAM asynchronous reads that don't need to go to clocks, but that's pretty high end. So for the most part, yeah, if you're talking about SRAM, you're talking about sync read mem. Good question. Yeah. Cool. Okay. So this is a lightning tour of the physical design concerns. And like I said, a few things to kind of walk away with this, right? Number one, if you're building hardware, know why you're building hardware. Even though it's fun, that's maybe why you're here, and that's why I'm here. Writing software for microcontroller or a processor is pretty effective at getting problems done, right? So you need to know why you need to build your own hardware for this or customize FPGA for this, right? And once you know why you're doing this, figure out what your metrics are, pick implementation technology, identify how you do kind of PPA targets. We talked about this very aspirational design methodology of having kind of this tool flow that's largely automated, and you kind of can iterate many times. As discussed, sometimes the tools aren't quite correct and need a bit of hand-holding. Rather than you giving them that hand-holding, you try and write scripts to do that for you, so that way you can kind of keep running it over and over again. And today we talked about a few different optimizations for memories, right? We talked about things like banking, traffic shaping, computation communication overlap, double buffering. But the big picture, of course, is the memory is a really important concern. It's more architectural concern rather than design concern, but it's still extremely important. That's why I have to be very smart about how you use your memories in your designs. You want to get by with the cheapest, slowest memories you can, but you can't always do that. Cool. Any closing questions? Okay, well, that's it. Please give Jose great questions for his Power Up lecture on Friday, and we're all excited for it. And if you didn't see the post on Slack, today I moved off from Friday to today, of course, but then next week we have another speaker coming on Monday who's going to talk to us about formal verification in Chisel. And because of that, I'm moving lectures around. So we're going to having our project design meetings move from Monday, Wednesday to Wednesday, Friday next week. And so as a result, I'm pushing back the proposal deadline from Monday to Tuesday. So let's go ahead and submit your project proposal by Tuesday, and in that way, we can be ready to meet with you on Wednesday and Friday to actually tell you what's going on. Cool. And we'll resume these kinds of lectures in what is that? That's in 4 lectures, right? All of next week and then after that, we'll start getting some more of these high-level design kind of conversations. Cool. All right. Have a good one, folks.